All right, so I will start again. So we ended sort of on this idea that too many too accurate statistics allow one to reconstruct the data, and that this notion of aggregate is hard to pin down. And so what we'll do now is we'll kind of get into ways of doing that, more formal ways of doing that. Okay, so all right, so differential privacy is one sort of formalization of this notion of aggregate that has been very successful both as a concept in the research community and sort of also just generally to help us understand what's going on in these problems. Okay, so the intuition behind differential privacy is that changes to my data are changes to my personal data should not be noticeable to users generally, and who are seeing the output. And so in some sense, the output is independent of my data. So differential privacy evolved from a line of work in theoretical computer science, really launched by a very nice paper of Dinur and Nissim that actually this reconstruction attack that I went through on the board came from. But it appeared in its sort of basically the form I'm going to give you in a paper of Dork, McSherry, Nissim, and myself. Okay. So to try and pin it down precisely, let's sort of lay a few basics down. So we're going to think of our data set as a vector of n values, a tuple of n values, in some domain D. And that domain could just be individual numbers, or it could be something more general like tax forms or categorical data or whatever. Okay. And for now, we'll think of x as fixed, not a random quantity. But there will be randomness in the picture, and the randomness comes from the randomization of the procedure A that analyzes the data, the algorithm that processes the data. And so for every fixed data set x, we get a random variable A of x. And the randomness in A of x might come from adding noise, it might come from resampling, could come from a bunch of different things. Okay, so to kind of pin down the definition, it helps to sort of have a thought experiment in mind. Imagine we start with our data set and change one person's data, or just remove that person entirely from the data set. Okay, either change their, and for this talk, the difference between these two models won't matter much, and it's probably usually, well, I'll use one or the other, either changing the data or removing them, depending on which is more convenient. The question we're going to ask is, when we make this change to the data set, does the distribution on outputs, this random variable A of x that now becomes A of x prime, how will that random variable change? Okay. So we'll say that data sets x and x prime are neighbors if they differ in one person's data. And the basic requirement is going to be that neighboring data sets should induce close distributions on outputs. Okay. So more formally, we'll say that the algorithm A is epsilon differentially private if for all neighbors x and x prime and for all subsets of outputs, the probability that A lies in any given subset S is at most e to the epsilon times the probability that A of x prime lies in the same subset. Okay, so for every event in the probability space, the probability of that event should go up by at most e to the epsilon. And because x and x prime are symmetric here, it also means it goes down by at most e to the epsilon. So implicit here is a particular metric on probability distributions where we're measuring change by the multiplicative change in the probability of any given event. Okay? And I'll come back to why this metric is a good one for this particular application, but just for now, I just want to kind of point this out. This is not sort of total variation distance or Kullback-Leibler or anything like that. This is a very specific metric that's a lot more sensitive than either of those. Okay, and then we'll also be talking about definitions. Sometimes we'll be talking about epsilon delta differential privacy, where we also allow for some additive term delta, where this delta should be really much smaller. Okay, so sometimes we'll use this kind of hybrid metric. Okay, so just a few remarks about the definition. First of all, this is a condition on the algorithm A that processes the data. Right? It's not a condition on how much distortion is introduced directly or anything like that. It's not that you can point to a particular output-input pair and say, oh, this is differentially private. You have to understand the process that generates the output from the input. The choice of distance measure on probability distributions really does matter, and I'll say a bit about that later. And you might ask what this epsilon quantity is, this first parameter here. And you should think of epsilon as sort of the main measure of information leakage of the algorithm. And epsilon is going to have to be not small, but not too small. So think of epsilon maybe as 1/10, generally not as a cryptographic style 1/2^100 or something like that. Okay. On the other hand, we've got this other parameter delta. And delta, when it occurs, should be interpreted as sort of the probability that things break down completely. That's not always exactly what happens, but you can think of it that way. And so delta really should be small. So think of delta as like 1 in 2 to the 50 and not 1 in 10. Okay, so epsilon can be small but not too small. Delta should be very small. Okay, so so this is going to be our working definition. Let's just work through a simple example of something that satisfies this definition, and we'll understand more about it. So, so the example is noise addition. So suppose that we've got some function of our data set that we actually want to compute. Okay, so some function f of x, and I'll think of x as returning a vector of real numbers, a p-dimensional vector of real numbers. So a simple example where p equals 1 is where I want to know the proportion of people who are diabetic in the data set. So there, for each person, I have a bit, which is either 0 or 1, and the thing I'm interested in learning is the sum of these bits. And a simple approach is to add noise to f of x. That is, how much noise. So a simple approach is to add noise to f of x, so we're going to release something like this. And the question is, how much noise do we actually need in order to satisfy differential privacy? What kind of noise? And the intuition is that we can add an amount of noise that is proportional to how sensitive the function f is to changes in its inputs. Okay. So specifically, given this vector-valued function f, we can look at what's called the global sensitivity of the function. So this is the maximum over neighboring data sets x and x prime of the L1 distance between f of x and f of x prime, where here this maximum really ranges over all possible neighboring pairs of data sets, not just neighbors of the data set we have. Okay. So for example, for the proportion of diabetics, the global sensitivity is 1/n. If I change one person's data in the data set, the proportion of diabetics goes up or down by almost 1/n. Okay. So the picture you should have in mind is that we're mapping, f maps data sets to vectors of real numbers, and this global sensitivity is a measure of how much distances between data sets get amplified or compressed by f. And if this is familiar to you, you can think of this as a Lipschitz constant in some appropriate metrics of the function f. I'm not going to use the terminology more than that. All right. So here's our main example, that if we, with the right distribution, what we can do is add noise which is proportional to this global sensitivity divided by the parameter epsilon. And I'm going to add that noise independently to each of the entries of the data set. Okay. So the specific distribution we're going to work with is called the Laplace distribution. So it's kind of a pointy version of the Gaussian distribution. So that's this blue curve here. And it has a parameter lambda, which is it's basically its standard deviation. It's a measure of how much noise we're adding. Okay, the standard deviation is actually square root of 2 lambda, but close enough. So again, we're adding noise that is proportional to this how much the function can change times 1/epsilon, where epsilon is how much privacy we want. And the reason this gives us this notion of differential privacy is that if we're comparing a of x and a of x prime, what we're looking at is the difference between two curves. One, the density of A of x is going to be the density of the Laplace distribution centered around f of x. And the density of A of x prime is going to be the density of a Laplace distribution centered at f of x prime. And those two, the centers of those two distributions differ by at most the global sensitivity. Okay? And the key key thing that's going on in key thing that's going on with these curves is that at all points, if I look at the ratio of h of y plus some offset delta over h of y, that is always in some interval given by, so it's always between a plus or minus delta over lambda, e to the plus or minus delta over this parameter lambda. And so what we get if we set lambda appropriately, when delta is the global sensitivity, we get that the ratio of the densities is always between e to the plus epsilon and e to the minus epsilon. Okay? So in particular, the probability of any set differs by a factor of at most e to the epsilon between the two distributions. Any questions about that? Okay, so again, this so there's no delta, there's no little delta in this version, this result. We just have epsilon. And so what we get again is that we can add noise proportional to this global sensitivity, and we're okay. All right, so so if we come back to our example of the proportion of diabetics, the global sensitivity of the proportion is 1 over n. What we're going to release is this proportion plus or minus some noise, which is on the order of 1 over epsilon n. So you might ask, okay, so this is differentially private. A natural question is, is this a lot of noise? Is this a little noise? Is this too much? How do we kind of calibrate our sense of whether or not this is acceptable? And well, one way to think about it is to sort of compare what we'd get if the data set were indeed a random sample from some underlying population. We're interested in understanding the underlying quantity. Okay, so if x is a random sample from some underlying population, then just due to sampling, the uncertainty of the sample we take, we expect this proportion to vary by roughly 1 over square root of n between different random samples from the same population. And so the amount of noise we're adding is very close, is small relative to this inherent variation. Okay? So if I were to plot the sampling distributions of the two quantities, namely the true proportion in brown and the quantity we're releasing in blue, those curves would be very close. Okay? Yeah, Lolita?
So how easy is it to find neighbors when you have to define this neighbor? If you had a very large data set, and is this really, can you prove optimality? What is the optimal mechanism?
Good question. Okay, so let's sort of one thing at a time. So neighbors in this case are defined by, again, changing one person's data in an arbitrary way. Okay, so in this case, the data for the proportion, each person's data is just a bit, so the kind of space of changes is pretty small. In general, computing. Let's just go back to this quantity. Computing this global sensitivity can be hard, and I'm not even going to. So we're going to look at functions where it's fairly easy to understand, or in some cases the research is figuring out, what this quantity is. As for your question, so it depends what you're trying to optimize for, and it depends at what level of generality you want an answer. If at the level of generality I'm presenting, if we're trying to optimize, say, the standard deviation of the noise we're adding or the expected L1 norm of the noise we're adding, so either expected L1 or L2, this mechanism is asymptotically optimal but need not be actually exactly optimal, meaning it's off by a constant. That constant actually goes to 1 as epsilon goes to 0. So for small epsilon, it's tight. I can give you citations. There's a paper by Pramod Vishwanath, who's actually a member of more of the information theory community on exactly this question. Yeah?
So in the past when I've heard a talk on this, sort of an actual question is why Laplace noise, why Gaussian noise, and then the answer given there is it's not in detail enough Gaussian noise, and maybe that Laplace noise is a better match or something like that.
Mm-hmm.
Is that accurate? And secondly, like if you perturb the metric slightly, is there a version where like Gaussian noise is better?
We'll come to Gaussian noise in 10 slides or so. The short answer is that what we're interested in is how, like, the multiplicative change in the probability of an event. And so this calculation becomes central. If you try to reproduce this calculation for Gaussian noise, what you find is as you get out into the tails, the ratio goes to infinity. Now that happens, it only happens out in the tails. It happens with small probability, so you can get this sort of epsilon, this hybrid epsilon delta guarantee, and I'll talk about that.
Here you have delta 0, actually.
So here delta is 0 in everything I've been saying. Okay, so that was an example. It's our first example, and we'll come back to it a few times. But sorry, the Laplace noise example. But let's just try to discuss the definition a little longer now, and then we'll come back to more algorithms that satisfy it. So useful properties. So here's this definition satisfies a number of useful properties. So one is that if I've got a bunch of algorithms that I want to run, these could be algorithms that are run all by the same person in sequence, chosen adaptively based on the outputs to previous algorithms, or they could be algorithms that are run by totally different people on overlapping data sets. If they are all individually epsilon differentially private, then their joint output is at most k epsilon, k delta differentially private. Okay, so the loss of information degrades gracefully as the number of algorithms increases, the number of releases increases. Okay? And it degrades at most additively. And in fact, it's better than that. You can get a degradation that increases roughly, I've kind of hidden one term here, but it increases roughly with square root of the number of iterations rather. So it increases sublinearly with the number of iterations rather than linearly. And we'll use that sort of stronger type of composition guarantee a couple of times. Okay, so here's our, so this is the sort of easiest thing to remember, and there's actually something a little better than that, k times epsilon. Okay, but maybe at this point all we need to remember is that as we sort of make more of these releases, the loss of privacy degrades gradually. Another sort of point to note here is that because this is a condition on probability distributions, it doesn't make any reference to the kind of underlying specifics of the underlying space that the random variables are defined over. If you sort of do something to the output of the algorithm, if you post-process it with by doing some other calculations, whatever you get will still be differentially private. Okay, if we'd use like the L2 metric on probability distributions, this wouldn't be true. But for this metric, so this is kind of a data processing inequality for this type of metric, if you want to think about it that way. Okay, and then the last thing that I think that is critical, given the stuff we were discussing in the previous part, is that this is meaningful. This definition gives us meaningful guarantees in the presence of arbitrary external information. Okay, and so let me try and explain what I mean by that. And yeah.
What are the external if you use total variation distance
We'll get there. Yeah. So you could use total variation distance, and I'll have a counterexample in a little while. Okay. So here's what given all the things we've been talking about, here's the kind of thing we might want from a data set, especially if you come from crypto or, for that matter, information theory. The thing you might want about your algorithm A is that you might help that whatever you knew about me ahead of time, before looking at the output of A, you'll know the same things about me after seeing the output of A. Right? This would be great. This would be saying that A tells you nothing about me ever. Okay, so this is unfortunately too strong to actually achieve. So it's impossible because these sort of correlation problems we were talking about earlier. Specifically, if you think of the smoking and cancer example, you want to learn the fact that smoking is correlated to cancer. Inevitably, that tells you something about people who smoke, if you didn't know that ahead of time. Okay, and this was formalized by Dwork and Noor, that this sort of smoking and cancer example is very general. Basically, any algorithm that releases useful information is going to have this type of issue where you can learn about people by learning about the population. And this was given a name by Kiefer and Machado Navachala. They call this a sort of a no free lunch result for privacy. Okay, so what about differential privacy? So differential privacy doesn't imply this, right? It can't. But what it implies is that no matter what you knew about me ahead of time, you'll learn essentially the same things about me, regardless of whether or not my data were actually used in the computation, regardless of whether my data were in the data set. So again, the thing we'd want is impossible, but what we can get is still pretty strong. Right? So it says that whatever you're learning is kind of independent of my participation in the data set. Okay. So let me give you a sort of a particular formalization of this that I think sheds light on, for this crowd, it will shed light on why the choice of metrics and stuff like that. Okay, suppose you're an attacker. You can think of you could sort of think of a Bayesian attacker, if you will, who has some knowledge ahead of time about the data set in the form of some prior distribution. Given an output little a, the attacker is going to draw some conclusions about the data set, and the conclusions he draws about point xi can be kind of encoded by the posterior distribution on xi, conditioned on the output. Okay. So now we can consider sort of two experiments. One is where we run the thing we expect to run, which is the algorithm on input the data set. And another experiment is where we run, let's call this experiment I, where we run the algorithm on the same data set with personized data removed. Okay. So again, we're sort of considering two settings. We start with the same prior and a particular output y, let's say, and now the conditional distribution. So in one case, you're going to run Bayes' rule to come up with your posterior distribution. You're going to run Bayes' rule with the posterior that y was generated from a of x. And the second case, you're going to run it with the posterior that y was generated from a of x with I removed. And I'm sorry, the PowerPoint ate the minus I. But basically, you're sort of getting two different posterior distributions, one when x was used, one when x without I was used. And the result, the statement is that if the algorithm is differentially private with delta sufficiently small, then these two posterior distributions are actually close. And they're close in essentially whichever metric you want to use. So they are kind of close in some multiplicative metric, which implies closeness in total variation distance. Okay. This type of statement does not hold if you try to use, say, mutual information as a measure of information leakage, or total variation distance as a metric on probability distributions. Yeah? You get a stronger result with delta 0 when delta is equal to 0, but I'm not going to explain the difference. I mean, yeah, you get a. There are differences, but they're at this level, they're not important. Yeah?
Another question about the basic definition. So one concern people would have about leaking data is not just what we did with the previous slide. It's not just about leaking my data
Yeah, okay, good. So I didn't mention this, but differential privacy implies some kind of group privacy, if you will. So if the Hamming distance between x and x prime is less than some number k, then the sort of if I look at the probability of any set, it goes up by the sort of this multiplicative measure goes up by a factor of at most k. And a similar statement is true with delta with non-zero delta, although it's messier. But morally, it's the same thing with non-zero delta. Okay, and that's by some kind of triangle inequality on probability distributions that you're sort of on this in this metric. Okay. All right. I have a feeling we're going to get through less than I anticipated in these 3 hours, and that's okay. All right. So just a little more about distance measures. So differential privacy is defined by this multiplicative distance, as we said earlier. It's tempting to use this total variation distance or say mutual information. This was Manoj's question a minute ago, and I said, well, one reason you can see that there's a problem is this sort of Bayesian formulation sort of falls apart if you try to use those metrics. But let me just give you, a specific example to make it really concrete. Consider the following sampling mechanism. So the sampling mechanism, what it does is it independently looks at each person's data and flips a coin. With probability epsilon, it publishes the person's data completely in the clear, and with probability 1 minus epsilon, it says nothing about that person. Okay. So in that case, if you try to use, say, total variation distance or statistical difference, you'd get a statistical difference between any two neighboring data sets of at most epsilon. Okay. The mutual information also between any given person's data and, assuming the data or come from a product distribution, the mutual information between a person and the output is relatively small. It's sort of epsilon times the entropy of the person's data to begin with. But in some sense, what's going on is like there are epsilon times n people who are guaranteed to be, I don't know which ones, but with overwhelming probability, about epsilon n of them will have their data published in the clear. Right? Yeah. No, there's a big difference between this and randomized response. And the difference is that here I'm either telling you that person's data completely in the clear or telling you I'm telling you nothing. Okay? So we're, even when the data are bits, it's erasure. Good. Yeah, sure. Thanks. It's erasure versus error. That's a good information theorist way to say it. Right. I like it. Okay. So the issue is that these measures are kind of average case measures in some sense, okay? Because they average over all possible outputs rather than, but even though any given output might, tell you a lot about lots of people, right? These measures will work as long as the set of people moves around, right? That's not to say that information theory has nothing to tell us about privacy. In fact, it comes up in a bunch of places, some of which I'll talk about, but it's not quite strong enough as a measure of privacy. The Lolita's talk tomorrow will say more about that. Okay. I'm going to move ahead because I'm like running way behind where I hoped I would be. I'll just say that there are a bunch of variations on this approach that have been considered in the literature. Okay, first of all, there were some predecessors to this notion dating back to this paper of Dinur and Nissim that we talked about earlier, and Cynthia Dwork was also involved in some of those that early work. Computational variance, variance where we try to assume something specific about what the adversary knows ahead of time. Various generalizations, and maybe Kamalika's talk will talk a little bit about that. And there are also access, sort of changes the access model. So the model we had with this sort of big centralized data set which collects all the data and then publishes stuff about it. That's a very simplistic model. You can consider lots of variants on it. They have been. I'm not going to tell you about everything. I just want you to know that these variants exist. OK, so that's differential privacy in a nutshell. At this point, it's become this sort of very broad and active field of research revolving around this definition and also its variants. So there are things that, there's a lot of work on developing algorithmic tools and techniques, and that's what I'm going to try to tell you about, and like some of in the remaining time. There are work on basic theoretical foundations, on feasibility results in learning, optimization, and statistics, lots of other places. There are connections to game theory and robustness and and false discovery. Sorry, I didn't mean to kind of actually hide information. There are a number of implemented systems. There are lots of algorithms that have been developed for like very specific applications. There are nice connections to policy where sort of you can use differential privacy as a kind of give you natural language standards you might want to try to use to think about data releases. And in some cases, explicit connections between differential privacy and legal standards. Like, for example, there's a project that Kobi Nissim, who's here, is involved in at Harvard on this. So it's kind of really spread out in a huge way. And again, there's really no chance I would, even if I were to move a lot more quickly, which isn't the point of a tutorial, even if this were a survey, I still wouldn't get through all of this stuff in 3 hours. But I just want you to sort of be aware of it. OK, so what I'd like to do for the time I have left is to focus on sort of algorithmic tools and techniques and give you some specific instantiations of things that we can do. And as I said, if we have time, some connections to other fields. And feel free to keep on stopping me. That's good. OK, so here's our, we're looking for algorithms. This is our question. What can we compute subject to this definition? Okay, so privacy is the requirement that a change in one input leads to a small change in the output distribution. What computational tasks can we achieve privately? And again, there's lots of work on this, and I'm going to try to give you just a flavor. Okay, so I'm going to switch slide decks because PowerPoint gets very unhappy when you put too many slides in one place. And so I kept on having problems with corrupted files, so I had to break it into several pieces. OK. So basic techniques. Let's look at our first one. This is the one we've already seen, noise addition. So let's just recap where we were. So we had this notion of global sensitivity of a function. What's the, we can add noise proportional to that global sensitivity. Let's just look at one more example. So we started off with proportions. Let me give you another example that's kind of where this technique does well, which is when we're looking at histograms. So suppose we've got n data points in some domain D. We want to partition D into little d disjoint bins. Suppose we have partitioned D into little d disjoint bins. And the function we're interested in computing is the histogram with respect to this partition. So how many data points fell into each of these bins? Okay. So if we think of this data set, if we think of this as a function of the data set, the global sensitivity of this function is either 1 or 2, depending on exactly the model we're working in. But if I think of somebody being inserted into the data set, then or removed from the data set, only one entry changes by at most 1. If I think of changing one person's data from bin A to bin B, then the L1 changes 2. In either case, it's a constant. And so it's going to be sufficient to add noise that's on the order of 1 over epsilon to each of the counts of this histogram and release that. Okay. So for example, here's an example of sort of blood types and things like that. So an example is, there are histograms on the line that are useful. You could consider like the population of the 50 US states would be an example, or EU countries, or French provinces, whatever your favorite example is. And then marginal tables also fit into this, where I'm sort of taking looking at, if I'm looking at a subset of the variables and asking how many people have, all ones in those for those attributes, or 0, 0, 0, 1 for those attributes, or each of the possible patterns. Because each person satisfies only one of the patterns, I get a histogram. Okay? Even though there are sort of 2 to the k numbers I'm releasing, where k is the number of attributes. Yeah? For histograms, actually, it is. Yeah. It's optimal for epsilon 0 differential privacy. Turns out for epsilon delta, it is optimal sort of in full generality, but if you make more assumptions about the data set, you can do better things epsilon delta differentially privately. I'm not going to have time to talk about that, but I can tell you about it offline if you want. So there's something that I think has been called the counting mechanism or something. I forget the exact name in one of Kobe Nassim's papers on learning that sort of generalizes this a bit. When delta is 0, this is really the best thing you can do. Again, it depends exactly how you define optimality, but for like reasonable notions of optimal, let's say you're trying to minimize the L infinity error or the L1 error or the L2 error between the sort of true thing and the thing you're releasing. This is optimal. I mean, maybe up to the constants aren't always exactly 1, but they could be 2 or something. Yeah.
One thing, I guess, related to the consistency thing.
Right.
So this histogram's not a valid histogram when you add noise.
No, it's not. It can have negative numbers. It can add to numbers that are greater than n. You can project afterwards to get something that is. You can sort of project back to the set of consistent histograms, and that will not make any like reasonable notions of error will not get worse if you do that.
I guess can you add different would you add different noise? I mean, going back to this optimality question, if I insist that the output actually have the right form, that it be a real histogram, I would try to add noise that lives in the space of histograms.
So. Like asymptotically, in terms of dependencies on d and epsilon, that wouldn't change anything. But you probably, for very specific, if when you're trying to optimize for the constants, the short answer is yes, almost certainly. But again, like you're not going to get these sort of broad, super broad optimality results.
Situation, if I want to actually implement this, this might make the difference between producing a garbage result or producing.
Yeah, hold that question for like an hour and a half. We'll talk about it. Yeah. Right.
Blood type is really like categorical data, so how do you add Laplace noise?
The counts.
Well, these are the counts, so I'm just looking at the bin counts, so in that sense. Okay, so it turns out lots of natural functions have low sensitivity. So histograms are an example. There are a bunch of others. And one of the nice things of the Laplace mechanism is you can sort of think of it as a kind of a programming interface where you ask a function, you get a noisy answer. You ask another function, you get a noisy answer. And a number of algorithms can be kind of formulated in that sort of as a sequence of low sensitivity queries. K-means is an example that gets used a lot. And this sort of, in some of the early systems that were implementing differential privacy, already kind of took this perspective, and they offered this kind of Laplace mechanism as a kind of a box you had access to, in addition to other mechanisms that one other mechanism that I'll talk about in a second. Okay, so the last thing I'll just say about noise addition is that you can consider sort of global sensitivity not in the L1 norm, but in other metrics. And as you vary the metric with which you're measuring sensitivity, depending on your function, the best metric to use might vary. You get different results. So, for example, if you care about L2 sensitivity, which is a very common case, it turns out that you can add Laplace noise, but a kind of a cleaner thing to do that's easier to think about is to add Gaussian noise, where the magnitude, the standard deviation of your Gaussian in each entry is on the order of this global sensitivity over epsilon. And now you've got this epsilon delta term, this delta term that crops in. You get a square root of log 1 over delta that appears there too. Okay. So this gives us epsilon delta differential privacy, but it allows us to work with the L2 norm, which is sometimes much better. And I'll just disagree with you on that one because I'm also keeping track. All right. So in particular, we can add noise on the order of like square root of d here, and Sorry, I skipped a step. So an example is that got covered by my slide, my animation, is imagine that I've got a sequence of queries now that are like counting queries where I'm asking how many people satisfy each of a given set of predicates. You know, how many people are diabetic, how many people are religious or whatever it is. So I've got this sort of vector of queries, kind of like what we had with reconstruction attacks. If I look at the sensitivity of this vector, it is in the L2 norm, it is on the order of square root of d. Because if I change one person's data, I've got a vector of d counts, each of which can change by at most 1. So the change in the norm is at most square root of d. And so what this tells me is I can add noise on the order of square root of d over epsilon to each entry, instead of what I would have gotten out of the Laplace distribution, which is d over epsilon. Okay, or out of the naive analysis of it. Okay. Okay, technically you can also get this same sort of a similar noise bound with Laplace noise using this strong composition theorem. But you know, as I said, it's kind of easier to understand with Gaussian noise. And coming back to those membership testing attacks we were talking about at the end of the last hour, those show that asymptotically this is tight, that it's sort of at this level of generality where you're looking at arbitrary sets of counting queries, you can't do better than this sort of square root of d over epsilon dependence. And if you normalize everything by n, you get square root of d over epsilon n, which is looks more like the bound we had in those previous slides. Okay. All right, so there are variants in these other metrics. There are also variants that kind of look at more local notions of sensitivity. So rather than caring about like what the worst case difference between f of x and f of x prime is, I might just care about how f of x varies in a neighborhood of the data set I have. Okay. It turns out doing that and satisfying differential privacy is delicate but possible, and there are a few notions you can use. I'm not going to kind of go into that, but just to let you know that one can do this. And so for functions where the local sort of notions of sensitivity are much smaller than this sort of global notion, you can do better than just sort of global noise. Yeah.
So I guess one way to think about this would be I do a test first to see what the local sensitivity is in an epsilon differentially private way, and then I run my local sensitive algorithm. Or is that the way?
One can use it that way. There are other ways, but that is. Yeah, so actually, I'm not going to, I have a whole talk ready about this, but I'm not going to give it. For graph data, many of the best algorithms use, where you're analyzing data that is itself a network, many of the best algorithms we know use exactly an approach like you say. That was sort of first formalized in a paper of Dwork and Lay, which is cited here, that specific approach. And it's been used a bunch of other times. And this sort of general idea was from a paper of mine with Kobe and Sofia Rasodnikova. OK, but I'm not going to go in. All right, so I wanted to talk about another basic algorithmic technique that comes up a lot, which comes from some kind of exponential sampling. Okay, so this idea was first suggested by McSherry and Talwar in a 2007 paper, and they're kind of the place they started is that, well, sometimes noise addition simply doesn't make sense. Okay, so maybe I'm releasing the mode of a distribution, right? Then what's the thing I add noise to if it's a discrete distribution? Or maybe I'm releasing a cut in a graph or a classifier or something like that, a decision tree, right? So there's no kind of inherent notion of noise. So their motivation was auction design, and I'll come back to that. But it's been applied very broadly, and it's kind of interesting independently of the application they had in mind when they first came up with it. OK, so let's look at it in a particular context. So imagine that we've got a data set. Each person's data, sorry, that should be x sub I. It somehow didn't get subscripted. X sub I is a set of websites visited by a Penn State student today. Okay, so this is my data set. So I've got some range of possible website names, but that, of course, there are a lot of them. And what we might want to do is, if we're trying to so we can sort of define a score function for each website, which is the number of students who visited that website. And our goal could be to output a frequently visited site, or more likely a list of frequently visited sites. Right? Okay, so we're looking, but let's just imagine we're trying to come up with one for now. We're looking for a site with y such that the thing we finally output is almost as good as the most frequently visited site. So deterministic algorithms can't be differentially private, because we're talking about sort of for each x we get a probability distribution on outputs. But so we could hope to get sort of really close to the best thing. OK, so noise addition in this context really is not going to work well. Because if I add noise to the lists of the frequencies of visit frequencies of all the sites, because each student can visit tons of sites, the sensitivity of that vector is going to be huge, and I'm just going to get meaningless results. Okay, but I can still do something meaningful, and that is I can output a website. I'll choose a website to output with probability proportional to, sorry, that really is like a huge typo. With probably proportional to the an exponential related to the score function. Sorry, let me just fix that. OK, let me try this again. OK, with probability proportional to e to the epsilon times this score. So I'm going to output, so I'm going to, OK, naively, I'm going to compute all of these scores. I'm going to raise them all to the eth power. I'm going to divide by something that makes them all add up to 1. I'm going to sample from that distribution. Turns out that's not the best way to implement it, but OK. So why is this a reasonable thing to even attempt? Well, more frequent websites are exponentially more likely to come up in this sampling than infrequently visited websites, right? OK, so sort of the intuition for utility of this algorithm is that, well, popular sites are like way more likely than rare ones. So like hopefully, what we're getting is like some curve that's correlated to the thing we're trying to optimize. And from the privacy point of view, well, one person's data can affect all of the scores, but can affect all of the scores by at most 1 each. So the idea is, OK, well, looking at the form for this probability distribution, the multiplicative change in the probabilities should be small. And indeed, that's the case. If I just try to analyze this mechanism, it is, as I specified it, it is 2 epsilon comma 0 differentially private. And you just figure that out by looking at the ratio of the probabilities of any given website under x and a neighboring data set x prime. That ratio is the ratio of these two, the things I was supposed to be proportional to, these two exponentials. And there's also the ratio of the normalizing constants that pops up. Each of those is off by e to the epsilon, so you get e to the 2 epsilon as your final privacy guarantee. Yeah?
So if the margin is large enough, I suppose I'm saying its local sensitivity is small. Maybe it's OK to deterministically.
Yeah, so I'm not going to spell that out, but the short answer is yes. As long as the margin is sufficiently large, you can get something epsilon delta differentially private by first looking at the margin. And when it is adding noise to the margin, which is itself a low sensitivity thing, and when that margin is large enough, outputting it. Yeah, so that is epsilon delta differentially private. And it's actually useful in a number of settings, which I'm not going to talk about. Yeah. Which kind of sampling?
Well, because this is a Gibbs distribution, right?
Yes. Give me a sec. Yeah. Well, I'll talk a little bit about it. No, maybe not as much as you want me to. All right. So, OK. So the other thing we can say is that this actually is useful. So what we're after, remember, for each x, so we've got some most frequently visited website. So what we're after is the kind of a website whose frequency is close to opt of x. What we get is that for any beta, the thing we output is, with probability at least 1 minus beta is greater than the optimum of x, minus the log of 1 over beta times the size of the range, the number of things we're selecting among, okay, over epsilon. So the important thing is that this scales logarithmically with the number of options we're considering. Right? So even if the number of options is large, the log of the number of options could, hopefully is not. And as Manoj's question suggested, in some cases you can actually get rid of even that term, but we're not going to do that. Okay, so why is this true? Well, you're just going to look at the set of good things, the things that happen that are, will define good G sub t. So think of these things as good sub, the good things measured by t. So those are the websites whose frequency is at least the optimum minus some slack t. And now we'll just look at the probability, the ratio of the probability of the not good things to the good things. And you can argue that that ratio is about the size of the range, at most the size of the range times e to the minus epsilon t, and then you just set t appropriately to get the statement in the theorem. Okay, so what does this give us? We get a mechanism that's epsilon differentially private, and it gives us some approximate argmax. Okay, so anytime you're designing a differentially private problem and you've got some like argmax-like thing to solve, this is the go-to first choice. It's not always the best, but it's usually where we'll start. And so more generally, Daniel, I'm watching time. More generally, this sort of this example of the websites is like very close to a fully general formulation. We've got some set of outputs. In general, we just need some score function whose sensitivity in terms of x is bounded. Okay, so it doesn't matter how it changes with y, it matters how it changes with x. And it's at most delta, and given x, we're going to sample from the same sort of probability distribution. I forgot to mention, you can also have some prior p of y on the probabilities. And jumping ahead to something I probably won't get time to talk about, a lot of procedures in Bayesian statistics can be kind of thought of as special cases of this thing, or vice versa, perhaps. And so there's this sort of some statistical procedures satisfy differential privacy automatically simply by virtue of being special cases of this. Okay, and then again, the sort of the general condition is we're going to get an optimality guarantee that just scales with delta. Okay, in the sort of automatic way, like there's no extra. You've basically seen the whole proof of this. Yeah. Did you have a question? Nope. So all right, hold it. Okay, so this mechanism, as I said, is fairly general. In fact, for epsilon 0, this mechanism is completely general. It turns out that like every differentially private mechanism up to a factor of 2 in epsilon can be viewed as an instantiation of this. So at that level of generality, you'd think maybe it's totally useless, but it turns out not to be. Like it turns out to be a very useful perspective on differentially private algorithms, and sort of it's used explicitly for learning, for lots of different problems, and sometimes implicitly for a number of them. Okay. Right. So this exponential mechanism, it is a special case of what's called Gibbs sampling. As such, it inherits like a number of information theoretic properties. One of them is that it is the mechanism that maximizes the expected score of the output conditioned on, subject to an entropy constraint, or conversely maximizes the entropy subject to a constraint on the expected score. It can be implemented for general like arbitrary sets of things. Implementing Gibbs sampling can be very tricky, and we're not going to talk about I'm not going to talk about that. But just one thing to bear in mind is that instead of sampling, one thing you can do that's algorithmically much easier to implement and numerically more stable is to add noise, the Laplace 1 over epsilon to each score. And so you compute all the scores, add noise to the scores, but just order of 1 over epsilon. And then pick the item with the largest noisy score. It turns out that gives you essentially the same distribution. In fact, if you sort of choose your noise carefully, it gives you exactly the same distribution. Yeah?
This doesn't get around the fact that if y is, say, exponentially large,
No. I mean, this...
it won't solve the complexity issue, right? You still have to...
No. You still have to explicitly compute all the scores. So for specific sets of scores, sometimes you can do something better, and we're not going to go there. One thing I did want to mention is that at the level of generality I presented it, this sort of, for the approximate argmax problem, this algorithm is optimal, and that attack of Dinur and Nissim that's on the board here actually shows that. So this result wasn't stated that way in the 2003 paper, but you can extract from this, basically you can carry out this attack by doing some kind of minimization or maximization, depending on, if you add a minus sign. And if you kind of translate the bounds you get from this into this setting, you'll see that this log of the range is actually necessary even for epsilon delta differentially private algorithms, because epsilon delta differentially private algorithms necessarily resist these types of reconstruction attacks. There are a number of generalizations of the exponential mechanism. There are variants that do better on specific classes of inputs, in particular for sort of histogram style things, where each person affects only one or a small number of scores. Also you can handle scores with different sensitivities in a kind of a nice smooth way. I'm not going to talk about that.